Okay, we are now jumping into our second to last chapter, people. Second to last, we're almost there. We're looking at chapter 10. We're looking, officially it's called molecular geometry, bonding theories. Two big pieces in here is switching from those two-dimensional Lewis structures into a three-dimensional model. And again, this is going to be critical for chapter 11, absolutely critical. And then also how this relates to what's going on a little more specifically in terms of chemical bonds. Now, just as a warning, there is some just base memorization that must happen. It's as it is. So we are bundling together 10.2, 10.3, 10.4, calling it the VESPR model. Stands for valence shell electron pair repulsion, but you don't need to know that. Anyway, electrons and molecules behave kind of like balloons. So imagine you're tying a whole bunch of balloons together. The balloons will naturally move. So because you can't have two balloons taking up the same space. So they kind of separate and create different shapes based upon how many balloons you have tied together. That's kind of what's going on with the electrons in a molecule. So if I have a single covalent bond, again, that's a pair of electrons directly between two atoms. We call things like that a bonding pair of electrons because, again, it's a pair of electrons involved in bonding, and those are found between the two atoms. Now, this is going to be a key term that I really want to stress. Any area that we find electrons is called an electron domain. Doesn't matter if it's a lone pair of electrons or a pair of electrons in a bond. Where the region we find electrons is called an electron domain. Now, a non-bonding pair of electrons or a lone pair of electrons would be also an electron domain. Now, one thing I want to be clear. A single bond, a double bond, and a triple bond are all one electron domain because that's one region between those two atoms that the electrons are found. So here's an example with ammonia. So we see ammonia would actually have 4 electron domains. There's one bonding pair of electrons up top. There's 3 different bonds. So each bond gives us 1 electron domain. The non-binding pair gives us an electron domain. So this would be a total of 4 electron domains. Now again, in general, every non-bonding pair and every bond or every multiple bond produces 1 electron domain. Okay. Now, because electron domains are negatively charged, they repel each other. And what actually happens is, as the domains repel each other, it reshapes how things are connected to that central atom. So the best arrangement of these electron domains around an atom is the one that minimizes the repulsions between them. And this is the idea behind the VESPR model. So when we look at the shapes, three-dimensional shapes that we see in VESPR, those are the shapes that come about because that's how the electron domains are best set up so that we are reducing the amount of repulsion. So here's what you need to know. What we see here on this page are electron domain geometries. So if there are 2 electron domains, doesn't matter what type, they will be 180 degrees from one another, and we call that arrangement of electron domain geometry linear. If there are 3 electron domains, they separate out by 120 degrees, and we call that trigonal planar. They all lie in one plane, so think of that as flat. 4 electron domains, like we saw with that ammonia, bond angle of 109.5, we call that tetrahedral. 5 electron domains, we call that trigonal bipyramidal. And it's 120 degrees, so it's basically like trigonal planar around the center, and then 90 degrees from top to middle. So it's almost like a trigonal planar and a linear merged into one. And finally, octahedral would be 4, so it's 6 electron domains, 4 end up being around that central axis, one on top, one on bottom, 90 degrees all around. Now, what you need to know is how the number of electron domains goes to the name and also the angles. So you need to know if there are 3 electron domains, that's called trigonal planar is the electron domain geometry, and that's an approximate bond angle of 120 degrees. That's what you need to know. So, again, this arrangement of electrons around that central atom, we call it electron domain geometry. Now, to contrast that, there's also what's called the molecular geometry, how it actually looks, because the molecular geometry, is specifically the arrangement of the atoms around a central atom. Now, again, electron domain geometry was counting atoms, and so kind of where bonds are, so it attaches to atoms, and where the lone pairs are. But molecular geometry differs from electron domain geometry if you have lone pairs. Now, and we'll go more into those in a bit. So VESPR model predicts the electron domain geometry. And from knowing this, and knowing how many of those domains are due to non-binding pairs, we can predict the molecular geometry. Think of molecular geometry as like a subset of electron domain geometry. Now, if all the electron domains in a molecule are from bonds, there's no lone pairs, then the molecular geometry will be the same as the electron domain geometry. But if one or more of those domains comes from lone pairs, then things start shifting. So, here's where things are at if we're obeying the octet rule. 2 electron domains has to mean 2 bonding domains. So it has to be linear, no exceptions. Now, if we have 3 electron domains, if all of them are bonding, so all are bonds, it's still called trigonal planar. Again, the electron domain geometry is exactly the same as the molecular geometry if they're all binding domains. But if there's 3 electron domains, but 2 are bonding and 1 is non-bonding, like we see here because there's this lone pair right there. Now what happens is, when we look at this molecule, we don't see this piece. That's just where some electrons are. So we say the shape is then called bent. Now, this is where the good news comes in, well, for you. If you are asked what is the approximate bond angle, the approximate bond angle stays the same within an electron domain geometry. So that means both this one and this one would have an approximate bond angle of 120. Notice I keep saying approximate, that's going to come into play in a bit. Next, if there's 4 electron domains, again, if all of the electron domains are bonding, same as the electron domain geometry, called tetrahedral. If 3 are bonding, 1 is non-bonding, then it's called trigonal pyramidal, like ammonia. If 2 are bonding, 2 are non-bonding, then it's also called bent. Water would be an example of that. So, again, an example. So ammonia, we've already done this. There's 4 electron domains around the central atom. So its electron domain geometry would be tetrahedral. Again, it would look like N, H, 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 and a lone pair. So that's 4 electron domains, 1 for each bond, 1 for the lone pair. So its electron domain geometry is tetrahedral. Now, I know that one of those domains is coming from lone pairs. So the molecular geometry would be trigonal pyramidal, because that's a subset of the tetrahedral electron domain geometry if there's 1 lone pair. Has to be memorized. So, steps using VESPR to predict the shapes of molecules. 1, you have to have the Lewis structure. Because without the Lewis structure, we can't figure out the number of electron domains. There's no shortcut here. Take your time and make the Lewis structure, period. Then count up the number of electron domains around that central atom. Determine the electron domain geometry just from purely the number of electron domains. Finally, use the arrangement of the atoms to determine the molecular geometry. In other words, look at how many of those electron domains are lone pairs. That's going to shift you. Again, if there's no lone pairs, then the electron domain geometry is the same as the molecular geometry. So, let's do an example. CO2. So let's draw the Lewis structure out for this. I'm going to go through the full process. So we have CO2. So carbon has 4 valence electrons. There's 2 oxygens, each with 6. So that's 12 plus 4 is 16 electrons. So carbon, oxygen, oxygen. I just used up 4. 1, 2, 3, 4, 5. There's 12 I used up because I used up 4. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. There is no electrons left over. So now I'm going to take a lone pair, make a double bond, take a lone pair, make a double bond. That is the Lewis structure of carbon dioxide. Now, how many electrons domain would there be around that central atom? So I look at the carbon, I see a double bond on the left, I see a double bond on the right. That is 2 electron domains. 2 electron domains means that the electron domain geometry for this is linear. The molecular geometry would also be linear because all those electron domains come from bonds. Okay. Now, notice I kept saying approximate bond angles. Those are the angles you need to memorize, but the true angles can differ from the approximate. So again, we're going to refine our VESPR model to predict and explain slight variances. Now again, you do not have to, if you're asked what is the approximate bond angle in this situation, go with the electron domain geometry bond angles. That's what there is. But if it tells you that something is different than what's from expected, this is how you explain it. So, for instance, methane, ammonia, water, they're all tetrahedral electron domain geometries. They all have 4 electron domains. But their bond angles are actually different. Methane has bond angles of 109.5. That's what we'd expect. Ammonia is 107, a little bit smaller. Water's 104.5, even smaller. Now again, if I asked you for the approximate bond angles for each of these, I would expect you to say 109.5 because that's the tetrahedral bond angle. But we now know because we're told these are actually a little bit different. Well, why is that? The difference is the types of electron pairs that make up the electron domains. So left would be methane, middle is ammonia, right is water. Turns out that non-binding electrons, the lone pairs, take up more space than bonding electrons do. So what happens is, as we get more and more non-bonding electrons, lone pairs, they take up more space and it squishes down everything else. So the bond angles are going to decrease as the number of non-bonding electron pairs increase. And again, that's because, again, those bonding electrons are attracted by both nuclei of the bonded atoms. So they're kind of stuck in between. But the lone pair of electrons, they're almost like those wacky waving arm inflatable guy things. There's waving all over the place. They're only bound to one location, so they take up more space, reducing the bond angles. Now again, because single lone pair has less nuclear attraction, because it's only bound to one atom, it becomes more spread out. So again, because it's more spread out, those lone pairs exert more repulsive force on other electron domains, again compressing or lessening the bond angles. So again, more lone pairs there are, smaller the bond angles are. That's what you need to know. Now, multiple bonds do a similar thing. Multiple bonds, like a double or a triple bond, have higher electron density than single bonds. So this also creates a larger electron domain. So if I have an electron domain made from multiple bonds, they're going to kind of act like the lone pairs. They take up more space. They're going to compress the angles. So multiple bonds, double or triple, will also decrease your bond angles. So for example, phosgene. So this is the molecule. So I see there around that carbon, there's 3 electron domains. There should be 2 single bonds, 1 triple bond, 1 double bond. I don't know why I said 3 single bonds. It's trigonal planar geometry. There's no lone pairs. So normally in trigonal planar geometry, we would expect 120 to be the bond angle. But this double bond here is taking up more space. So it's going to compress things down a little bit. So it turns out that these top bond angles get spread out to 124.3. The lower ones get compressed to 11.4. Again, you would never have to be expected to expect those numbers, but you would be expected to know why those numbers are there. Now again, how do these all compare in terms of volume? Who compresses the most? Lone pairs compress the most. Then triple bonds, then double bonds, then single bonds. Now, if a molecule has an expanded octet, meaning it's violating the octet rule, it has more than 4 electron domains. We can work with that too. So again, we can do that. So you have to memorize these as well. So if there's 5 electron domains, again, the electron domain geometry is trigonal bipyramidal. If all are bonding, we call it trigonal bipyramidal, same as before. If 4 are bonding, 1 is non-bonding, we call it seesaw. Because if you actually tip that on its side, if you imagine that kind of rotating forward a little bit, it looks like a seesaw. If 2 are non-bonding, then it's T-shaped because it looks like a T. And if 3 are non-bonding, we call it linear. Same with 6 electron domains. If they're all bonding, it's called octahedral. If 1 is bonding, it's called square pyramidal. You can see the little picture there. If 2 are non-bonding, we call it square planar. And then we could have 3 are non-bonding, we'd go back to T-shaped, and then linear, and it just kind of goes off on that. You have to have these memorized. There is no shortcut around it. Pure brute force memorization is what is required. So we're going to predict the electron and molecular geometry of ClF3. So first we're going to draw the Lewis structure. So ClF3, chlorine is 7 plus 3 times 7, so that's 21. So we're looking at 28 electrons. Draw the basic structure. Chlorine, fluorine, fluorine. I had 28 electrons. I just used up 6. 22, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. So I used up 18. That leaves me with 4 left. Where do those last 4 get dumped? They get dumped on the central atom. So 1, 2, 3, 4. I'm out of electrons. Now, looking at that chlorine, I see, I'll do this kind of in yellow, 1, 2, 3, 4, 5. I see 5 electron domains. Because it's 5 electron domains, that means we would be expecting trigonal bipyramidal as our electron domain geometry. But we'll get there in a moment. Anyways, so I've done that. How many electron domains? There was 5. 5 electron domains, trigonal bipyramidal, just like I said. How many were bonding domains? 3 of them were bonding, 2 non-bonding. So that means its molecular geometry, checking that chart, would be T-shaped. Again, if 1 were bonding, yeah, anyway, you saw that. Would be called T-shaped. Now, shapes of larger molecules. So we can actually extend the VESPR model to a more complex molecules than just something with a central atom. So consider acetic acid here. Here's acetic acid. There's actually 3 kind of central atoms here. there's carbon number 1, carbon number 2, and that oxygen right there. Those are all central atoms. So we can actually view this from the point of view of each of those. So we can look at the VESPR model to look at each individually. So looking at this carbon on the left, I see 4 electron domains. They're all bonds. So its electron domain geometry would be the same as its molecular geometry, or tetrahedral, and that's 109.5 degrees. The central one, I see 3 electron domains, single bond, double bond, 3 electron domains. So trigonal planar. So we'd be seeing approximate bond angles of 120. Finally, on the right here, I see 4 electron domains, 1, 2, 3, 4. So we're back to tetrahedral. But this time, because 2 of those are non-bonding, so if I have tetrahedral with 2 non-bondings, that's where we get bent. So now that we have the shapes, and especially, I'm going to be very clear about this, especially that idea of that lone pairs and that influencing the shape that we see in the molecular geometry, we can tackle section 10.5, molecular shape and how that affects bond polarity. Now again, remember that bond polarity is all about how equally electrons in a bond are shared. A nonpolar bond would be equal sharing. Polar bond would be not equal sharing. Now, what lets us know this is the greater the electronegativity difference, the greater the bond polarity will be. So, the dipole moment, which is created, again, just as a measure of that polarity, depends upon the polarities of both the bonds and the geometry. So again, it's not enough just to have a polar bond, to have a polar molecule. The geometry also comes into play. Now, for every bond, we can look at the bond dipole. That's just the polarity of that bond. Is there equal sharing or not? And again, the dipole moment is due only to the 2 atoms in the bond and their electronegativity difference. So for example, CO2. This would be the Lewis structure without the lone pairs around the oxygens of carbon dioxide. Each CO bond is polar. Oxygen is substantially more electronegative than carbon is. But we also have these 2 carbon-oxygen bonds. The bonds are identical. They're both carbon-oxygen double bonds. So what ends up happening is for each bond, we end up with a high electron density around the oxygen, low electron density around the middle, because the oxygens are more electronegative. Now, this is where it gets interesting. Bond dipoles and dipole moments, don't stress over the difference right now, are vectors. As you may have learned in your math classes, is that vectors are something with an amount and a direction. So the overall, the molecular polarity, or the molecular dipole, is the sum of all the bond dipoles that make it up. That sounds confusing. Basically, what this comes down to, for the molecule, we have to consider not only the sum of the individual dipoles, is each bond polar, but we have to consider the direction of it. And it turns out that polarities in opposite directions cancel. Polarities in the same direction add up. So with that carbon dioxide, so again, back up here, if I was to write that, So again, oxygen's more electronegative, so electrons get pulled to the right, electrons get pulled to the left. The electrons are being pulled left and right equally, but the directions are opposite. And so what actually happens is the individual dipoles cancel. So from the geometry of carbon dioxide, we would say it's a nonpolar molecule. Even though there are polar bonds in it, the molecule as a whole is nonpolar. Now to contrast this, here's water. And water would have lone pair, lone pair. So in water, if we notice, we have electrons being pulled up towards the oxygen, electrons being pulled up towards the oxygen. So there's electrons getting pulled left and right. The left and right parts cancel, but there's only electrons being pulled up in both cases. So the net result is water is a polar molecule because there is this net polarity upwards of electrons being pulled, leaving the top end, the oxygen side, with a slight negative charge, the hydrogen, the bottom side, with a slight positive charge. Now, steps to determine molecular polarity. 1, draw the Lewis structure. 2, figure out the molecular geometry. 3, look at the effects of electronegativity differences. In other words, is each bond polar or not? Here's the simple version. If all of the atoms around the central atom are the same, in other words, like with carbon dioxide, it was 2 carbon-oxygen bonds. Or with the water, there's 2 oxygen-hydrogen bonds. If all the bonds are the same type of bonds, that means the amount of polarity is the same. Now, it turns out that for things to not cancel out fully, in other words, for there to be polarity, lone pairs are necessary. So again, you have to have a difference in electronegativity. You have to have lone pairs on the central atom. If those two things are not met, it is not a polar molecule. If both of those things are met, it's a polar molecule. So again, both things have to be met to be polar. To be polar, you have to have polar bonds, and you've got to have lone pairs. If both are met, it's a polar molecule. So now we're getting into kind of the theory behind bonds. So again, VESPR gives us a method to predict the shape, but doesn't explain why the bonds exist. Now, if we mix together Lewis's notion of electron pair bonds and the idea of orbitals, it gives us a model of chemical bonding. We call this valence bond theory. Now, in Lewis theory, covalent bonding occurs when atoms share electrons. And this sharing concentrates that electron density between the two nuclei involved. In valence bond theory, we say there's this buildup of electron density between the nuclei, same idea, when a valence atomic orbital of one atom is going to merge with a valence orbital of another atom. So again, it's saying that this sharing of electrons is actually due to an overlap of orbitals containing electrons. Now, with this merger of orbitals, meaning that they share a region of space, we call that overlap, creatively named, I will say. This overlap of orbitals will allow 2 electrons of opposite spin to share the common space between the nuclei. That's the bond. So here would be an example of this sulfur-hydrogen compound. So we see hydrogen, we see sulfur. Again, then we see those kind of 3 pairs. That's those 2p sublevels. And we are overlapping like a hydrogen's 1s with one lobe of the sulfur's 2p. And then we do that same thing here. This overlap of the orbitals is what's forming the bond. Or like that with 2 hydrogen atoms. Now, distance-wise, there's always going to be an optimum distance between the 2 nuclei in a covalent bond. Too close, the nuclei repel. Too far away, not enough overlap, not a strong bond. We need that overlap for there to be a good bond. So there's an optimal distance, and that's what forms. Now in section 10.7, we're going to look at something called hybrid orbitals because it gets a little bit more complex than just orbitals overlap. So again, orbital overlap works for explaining covalent bonds, but it's difficult to extend to polyatomic molecules or more complicated molecules. Now, when we apply a valence bond theory to polyatomic molecules, not just polyatomic ions, polyatomic molecules, we must explain the formation of these electron pair bonds and the geometries. So how do we get those weird geometries that we see? Well, what we actually assume happens is that the orbitals in an atom reform and mix to form new orbitals. We call those new orbitals hybrid orbitals. And those hybrid orbitals exist purely for the sake of bonding. The shapes of hybrid orbitals and the angles of hybrid orbitals are different from the shapes of the originals. The shapes of these, you almost imagine it, they basically look like a bowling pin. You're going to have a really small end and a really big end. So you get a little small end, and a big end with the kind of nucleus there in the center. And the point of them is because you now get this big end here. This is where the overlap happens. So you're maximizing the overlap space, so you get a better bond. The process of forming hybrid orbitals is called hybridization. Now, it's thought is that orbitals will hybridize with each other just before they bond, in preparation for bonding. Now, when hybridizing, the total number of orbitals remains constant. So, however many atoms or orbitals were involved originally, or let's say hybrid orbitals, so if you have 3 hybrid orbitals, that means that 3 orbitals mix together to form 3 hybrid orbitals. Now, as we look at the common types of hybridization, what I want you to focus on is the type of hybridization, in other words, the name of it, and how that relates to the electron domain geometries, because that's the secret. I'll give the secret away right now. Anytime we see a specific type of electron domain geometry, that corresponds to a specific type of hybridization, period. And again, electron domain geometries would be linear, trigonal planar, tetrahedral, trigonal bipyramidal, octahedral. We're not even going to worry about these last 2. We're only going to worry about the first 3, linear, trigonal planar, and tetrahedral. So, first type that we see is called an sp hybrid orbital. This is a mix of a single s and a single p orbital. I'm going to say single because not to get confused with energy level. A single s orbital and a single p orbital, that's 2 orbitals, hybridized together to make 2, that's a pair of sp hybrid orbitals. So again, it forms when an s orbital is hybridized with a p orbital. And we get 2 things that look like this in opposite directions. There's that kind of bowling ball shaped thing. And they are spaced so that they are pointed 180 degrees away from each other, which is the directions we see for linear electron domains. So here's the deal. 2 electron domains equals 2 hybrid orbitals equals sp hybridization. And again, sp, there's 2 things there. Now, how do we make this? So again, what's going to happen is, I'm going to show this as we go. We're actually going to promote an s electron into a p orbital. This takes energy. Now, if it takes energy to promote the electron, why does it hybridize in the first place? Again, hybrid orbitals have that one really large lobe, which again can be directed better at unhybridized orbitals, creating better overlap. And the better overlap you create, the stronger the bond is, the more energy that's released. So it's worth it. I'm going to show kind of how that hybridization and promotion works on the next one. You don't really need to worry about that too much. Now, the next type is sp2. Now, one thing I want to notice. sp2, that's S and P2. There's 3 things there. So an SP, so again, a single S and a single P gives 2 sp orbitals. So let's say boron trifluoride, don't worry about the structure, we get a 2s electron is promoted to a vacant 3p orbital. We're going to mix a 2s and 2p's. So how many total orbitals are we mixing? So that's a single s and a pair of p's. That's 3 orbitals. So we're going to get 3 sp2, and again sp2, that sp2, that's 1 plus 2 equals 3. So again, that's what we see here. So if I look at boron in its valence configuration, I would see 2 electrons in the 2s, 1 electron in the 2p. We're going to promote this electron, so it goes up here. Then we're going to hybridize these 3, forming 3 sp2 orbitals and leaving us 1 empty 2p orbital with nothing going on. Now, when you have sp2 orbitals, again, that's 3 orbitals mixing together, a single s and 2 p's, hence sp2. You're going to get 3 shapes off of this, 3 different angles. That looks confusing. Together, it looks like this, 120 degrees. Well, where have we seen 120 degrees? Oh, that's right. That's trigonal planar. Trigonal planar was 3 electron domains. That equals sp2. Anytime we have trigonal planar, anytime we have 3 electron domains, we have sp2 hybridization. That's what you need to know. Finally, sp3. So let's even look at this, sp3. So it's formed from a single s and a trio of p's. So how many orbitals in total? 1 plus 3 is 4. It's 4 electron domains. So we get 4 sp3 orbitals. We see the same hybridization thing going on. I kind of forgot one here. Doop-a-doop-a-doo. There's 4 of them. Again, that shape should look familiar. This would be tetrahedral, 109.5 degrees. So again, 4 electron domains equals tetrahedral equals sp3 hybridization. That's what you need to know. Don't make it harder than it has to be. Anytime we see 2 electron domains, that's linear, that's sp. I see 3 electron domains, that's trigonal planar, that's sp2. I see 4 electron domains, that's tetrahedral, that's sp3. Doesn't matter how many of those electron domains are bonding or non-bonding, doesn't matter. Does not matter. So again, in summary, hybrid orbitals gives a model of how it shows how structures in atoms are predicted. Don't make it harder than it has to be. Orbitals go together in the shape of their hybrids, which means that again, it's tied directly to the electron domain geometry. So again, draw the Lewis structure, find the electron domain geometry, and then look at what type of orbitals, hybrid orbitals, are needed to accommodate that. So again, if it's linear, 2 electron domains, sp. Trigonal planar, 3 electron domains, sp2. 4 electron domains, tetrahedral, sp3. That's it. Now, what's going on when we have multiple bonds? This is interesting. So far in covalent bonds, we viewed this electron density to be between the 2 atoms. We call that sort of bond a sigma bond. So that sigma bond is this overlap of those hybrid orbitals. And that's that overlap between the 2 atoms. Anytime you have a bond, there is a sigma bond. Single bonds are just a sigma bond. So, now that we have that, what if there's multiple bonds? we need another type of bond because there's no more room in the middle. The sigma bond's taking up the space in the middle. So we need a separate place for those other electrons, for those bonds to form. So they have to be where the sigma bond is not. We call this other type of bond a pi bond. And a pi bond, a single pi bond, is an overlap formed above and below the axis formed by the nuclei. In other words, above and below the pi bond. And what this is done is created by an overlap of p orbitals. Now, it's going to be less overlap than with sigma. Again, the sigma bond was done with those hybrid orbitals, and hybrid orbitals are specifically made to facilitate overlap. P orbitals aren't. It is generally going to be a lot weaker than a sigma bond, but it's better than nothing. So here's kind of an example. So here is C2H4, it looks like. There's a double bond there. So there's this sigma bond in the center. And then there's this p orbital overlap. Both sets, the top and the bottom overlap, that is one pi bond. So again, there's a sigma bond in between. And then this upper and lower piece together makes up the pi bond. If there's a triple bond, like we see here with C2H2, then you get that hybrid. In this case, there's an sp because it's linear. Because again, two electron domains. So it's linear, so we should be seeing sp hybridization. That's what we see. There's that sp hybridization, sp. And this case, you actually get two pi bonds. One above and below, and one front and back. So again, provides more overlap. So what type of bond? Generally, this is what you need to know. Single bonds are sigma bonds. Period. Done. Double bond will be one sigma, one pi. Triple bonds will be one sigma, two pi. That's what you need to know. Now again, what does this all mean? What's the importance of that pi bond? Now, because they lie outside the axis between the nuclei, because again, they're above and below the atoms, they need to remain parallel. And so they actually provide support to the molecule. It keeps it from twisting. If all you have is a sigma bond, it's like things that are connected by just a single spoke. They can twist around. But the more support you give them, that's what the pi bonds are doing. They're adding more support. The more support there is, the more rigid the molecule becomes. Now, there's an interesting thing that happens with pi bonds in resonance. So if a molecule has resonance, its pi bonds can actually extend for more than the two bonded atoms. So this is actually what's happening in resonance. We call this delocalized pi bonding. And I have a picture of this on the next slide. Sigma bonds stay the same, but, so here is hexane. So we have all these sigma bonds kind of in the center, same as before, those don't change, but now these p orbitals start overlapping with one another. And as they start overlapping with one another, the electrons can actually cruise around in those overlap regions. So that's why you get that kind of shift of where that single bond is, because actually those electrons are moving around between those different locales, hence delocalized. And that's what's actually happening in resonance. And that is the chapter.